Hello everyone and welcome to very first video in our series on the fundamentals of digital design and Verilog. I'm so excited you are here to start this journey with me. Today we are kicking things off with the absolute basics. Have you ever wondered how computers, phones and every other digital device can understand and process everything from the text to image and image to music? It all comes down to a special language of numbers that they use to communicate. In this video, we are going to demystify this language. We will dive into the core number systems used in digital electronics, that is, decimal, binary, octal, and hexadecimal. And most importantly, I will show you step by step how to convert numbers between them. By the end of this video, you will have a rock solid foundation that's essential for everything we will learn in this series. Alright, so let's start with the definition of number system. Number system is a way of representing numbers using a set of symbols and a base. The base determines the number of unique digits used in the system. Importance of number system in digital electronics. Digital systems like computers fundamentally operate using only two states, that is on or off, high or low, which are best represented by binary digits, that is 0 and 1. While binary is the machine language, humans find it cumbersome to read long strings of zeros and ones. Therefore, octal and hexadecimal systems are used as shortened representation for binary numbers as they are easily convertible to binary. Now that we understand why number systems are so important, let's look at the four main types we will encounter in digital electronics. First up, we have the decimal number system, also known as base 10, the most common number system used by humans. It uses 10 unique digits. They are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Each digit's position represents a power of 10. For example, express a decimal number using powers of 10. We have example of 325. So, to find the decimal number, we need to multiply by 10 powers. 3 into 10 to the power 2 plus 2 into 10 to the power 1 plus 5 into 10 to the power 0. That is 300 plus 20 plus 5, that is 325. Next we have binary number system base 2, uses two unique digits 0 and 1 called bits, binary digits. This is the native language of computers. Each digit's position represents a power of 2. For your knowledge purpose, bit a single binary digit 0 or 1, nibble means 4 bits, byte means 8 bits, MSB is the most significant bit, the leftmost bit in the binary number, representing the largest value. LSB is the least significant bit, the rightmost bit in the binary number, representing the smallest value. For example, we have convert 1011 base 2 to the decimal. We need to multiply by powers of 2. 1 into 2 to the power 3 plus 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 1 into 2 to the power 0. That is 8 plus 0 plus 2 plus 1, 11. So the decimal value of 1011 is 11. Next we have octal number system, also known as base 8, uses 8 unique digits. Each digit's position represents a power of 8. A compact way to represent binary numbers as 3 binary digits can represent one octal digit. For example, convert 53 to decimal. 5 into 8 to the power 1 plus 3 into 8 to the power 0. So 40 plus 3, 43. The decimal value of number 53 is 43. Next we have hexadecimal number system, also known as basic. Uses 16 unique symbols 0 to 9 and A, B, C, D, E, F. A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. Each digit's position represent a power of 16. An even more compact way to represent binary numbers as 4 binary digits can represent one hexadecimal digit. For example, we have convert to F to decimal. F is 15 as we know. We need to multiply powers of 16 into given numbers. So 2 into 16 to the power 1 plus F into 16 to the power 0. 2 into 16 plus 15 into 1, that is 32 plus 15 is equal to 47, and the 47 is the decimal form of 2F. Now that you are familiar with the different number systems, the next logical step is to learn how to convert between them. This is one of the most fundamental skills in digital design. We will start with the most common and important conversions first, and I will show you the exact method and steps to perform then. First, let's tackle decimal to binary conversion. Third one is integer part. Repeated division by 2, collect remainders from the bottom to top. Method 2 is fractional part. Repeated multiplication by 2, collect integer parts from top to bottom. Let's take a example 1. We are going to convert the decimal number 25 to its binary equivalent using simple repeatable method called repeated division by 2. We start with our number 25 and we divide it by our target base, which is 2. 25 divided by 2 is 12. With the remainder of 1, we are going to save that remainder, point to the first line and the one next to LSB, that is least significant bit or the first bit in the our final answer. Next we take the result of our division, which is 12, and divide it by 2 again. 12 divided by 2 is 6. With the remainder of 0, we save this remainder, point to the second line. We continue this process. 6 divided by 2 is 3 with the remainder of 0, point to the third line. 3 divided by 2 is 1 with the remainder of 1, point to the fourth line. And for the last step, we divide the final result 1 by 2. This gives us 0 with the remainder of 1, point to the last line, that is MSB, the last bit in our answer. Now to get our final binary number, we simplify read the remainders from the bottom to top. Last remainder was 1, the MSB, then 1, then 0, and finally 1, the LSB. When we put them all together, we get 11001. So the decimal number 25 is equal to 11001 in the binary. This method works for converting any decimal integer to binary. Example 2. Let's learn how to convert fractional decimal numbers to binary. For this, we use the repeated multiplication by 2 method. We begin with our fractional number 0.625 and we multiply it by 2, which is our target base. As you can see, 0.625 times 2 equals 1.250. The key here is to look at the integer part, which is 1. This is the first bit of our binary answer. Next, We take only the fractional part of the result, which is 0.250, and multiply it by 2 again. 0.250 into 2 equals 0.250 times 2 equals 0.500. The integer part this time is 0. This is our second bit. Finally, we take the new fractional part 0.500 and multiply it by 2 one last time. 0.500 times 2 equals 1. The integer part is 1. This is our third bit. We stop when the fractional part becomes 0.000. To get the final answer, we read the integer parts from top to bottom in the same order we found them. Our integer parts were 1, then 0, and then 1. So, when we put them together, we get 0.101. Therefore, the decimal fraction 0.625 is equal to 0.101 in binary. The next conversion is binary to decimal conversion. Multiply each bit by 2 position starting from 20 for the rightmost bit and sum the results. For example, we need to convert 1011.01 base to decimal. Break the number into integer and fractional parts. Integer parts, multiply it by base of 2 and you will get it as 11, and fractional part you just multiply it by 2 to the power minus 1, the negative of power, then add both the integer part and fractional part. You will get it as 11.25 base 10, that is decimal form of 1011.01 in binary. Next conversion is decimal to octal conversion. Repeated division by 8. Collect remainders from the bottom to top. For example, convert 120 to octal. Step by step division by 8 as shown in the figure. 120 divided by 8, that is 15. Remainder is 0. Then this is the LSB, which comes in third place, and 15 divided by 8, that is 1, remainder is 7. This comes in second bit. 1 divided by 8, that is 0, remainder is 1. So this is the MSB first value, and read the remainders from bottom to top. 170 is the octal conversion of decimal 120. The next conversion is octal to decimal conversion. Method is to multiply each digit by 8 position and sum the result. Convert 170 to decimal. We need to multiply it by powers of 8. 1 into 8 to the power 2 plus 7 into 8 to the power 1 plus 0 into 8 to the power 0. So we'll get it as 120. This is the decimal form of octal 170. Next conversion is decimal to hexadecimal conversion. Repeated division by 16. Collect remainders from the bottom to top. Converting 10 to 15 to A to F. Convert 255 to hexadecimal. We need to divide it by 16. So 225 divided by 16 is 15. Remainder is 15. So F is the LSB. Then 15 divided by 16 equal to 0. Remainder is 15. That is F, MSB. Read remainders bottom to top. That is FF is the hexadecimal form of decimal 255. Next conversion is hexadecimal to decimal conversion. Multiply each digit by 16 position and sum the result. Remember to convert A to F to 10 to 15. Convert FF to decimal. We know that f is 15 in hexadecimal. Then we need to multiply by powers of 16. F into 16 to the power 1 plus f into 16 to the power 0. By adding, we'll get 255. That is the decimal form of FF hexadecimal. Next conversion is binary to octal conversion. Group binary digits into sets of 3 from the right, add leading zeros if needed, convert each group to its octal equivalent. For example, convert 1101011 to octal. First step is group binary digits into set of 3, that is 001, 101, 011. We paired with leading zeros to make full groups of 3. Step 2. Convert each 3-bit group to octal. 001 is 1, 101 is 5, 011 is 3. Then we'll get as a result 153 is the octal form of binary 11011011. The next conversion is octal to binary conversion. Convert each octal digit into its 3-bit binary equivalent. Convert 153 to binary. Convert each octal digit to 3-bit binary equivalent. 1 is 001, 5 is 101, 3 is 011. Combine the binary groups, that is 001, 101, 011. You can drop leading zeros, so we'll get output as 1101011. This is the binary form of octal 153. Next conversion is binary to hexadecimal conversion. Group binary digits into sets of 4 from the right, add leading zeros if needed, convert each group to its hexadecimal equivalent. For example, convert 110, 111, 101 to hexadecimal. Step 1 is group binary digits into set of 4. So write it as from right to left 0001, 1011, 1101. Paired with leading zeros to complete 4-bit groups. Convert each 4-bit group to hexadecimal. 0001 is 1 in hexadecimal, 1011 is B, 1101 is D. So we will get the result as 1BD hexadecimal. Next conversion is hexadecimal to binary conversion. Convert each hexadecimal digit into its 4-bit binary equivalent. Convert ABD to binary. Step 1 is convert each hexadecimal digit to the 4-bit binary value. 1 is 0001, B is 1011, D is 1101. Combine the binary groups. You can drop leading zeros. Then we'll get the result as 1101, 11101. Later we'll get the result as 1101, 11101 in the binary form, which is the conversion of 1BD in the hexadecimal. The summary of number system conversion is: first we take decimal to any other bases like binary, octal and hexadecimal. We need to divide and write the remainders backward. Continuously divide your decimal number by the new base. For example, divide by 2 for the binary, 8 for the octal, 16 for the hexadecimal, and keep track on the remainders at each steps. Your new number is the sequence of the remainders. Read from the bottom of last remainders to the first. Any other bases to decimal, we need to multiply by powers and then add. Take your number and starting from the rightmost digit, multiply each digit by its base, rise it to a power. For example, 2 to the power 0, 2 to the power 1, 2 to the power 2 for the binary. Add all the results together and sum is your decimal number. Then binary, octal and hexadecimal. In this case, binary to octal, you have to group the bits in threes. Start at the rightmost bit of your binary number and group the bits into set of 3. If the last group on the left has a favor, then 3 bits, add leading zeros. Convert each group of 3 bits into single octal digit using a lookup table. For example, 101 is 5, then 011 is 3. Octal to binary, each digits comes 3 bits. Take each octal digit and replace it with its 3-bit binary equivalent. For example, 6 becomes 110, 2 becomes 010. Combine all the binary groups to get your final number. For binary to hexadecimal, group bits in fours. Start at the rightmost bit of your binary number and group the bits into set of 4. If the last group on the left had fewer than 4 bits, add leading zeros, convert each group of 4 bits into single hexadecimal digit. For example, 1101 is D, 1010 is A. For hexadecimal to binary, each digit becomes 4 bits. Take each hexadecimal digit and replace it with its 4-bit binary equivalent. For example, C becomes 1100, 5 becomes 0101. Combine all the binary groups. And that's it. You have just taken your first step into the world of digital design by mastering number systems and their conversions. This is the crucial skill, and I hope this video has made these concepts clear and easy to understand. If you found this video helpful, please give it a thumbs up and consider subscribing to the channel Byte and Build so you don't miss out on the next videos in our series. In our next video, we will build on this knowledge and move on to our next topic. Thank you so much for watching, and I will see you in the next one.